Hello everyone. So I have decided to make a recording of the solutions for the problems, suggested problems for chapter 37, or at least for the first batch. The reason for this is, well, we have very limited time for a station. I don't want anything to be skipped. And also we have our final exam right after the classes are over, so we won't have time for an additional station session. I'm trying a format here, so hopefully this will be useful, but I do appreciate if you provide me some feedback on how this format works. Okay, so there are quite a number of suggested problems for this chapter, and I wrote them here. So we start with problem number 3. It's reasonably simple. It's sort of like a warm-up problem. So we have a hydrogen chloride molecule that vibrates with an initial frequency of 8.1 times 10 to the 13 Hertz. What's the difference in energy in joules and electron volts between successive values of the oscillation energy? Okay. All right, so let me take a pen here. So this is problem number 3. We have a hydrogen chloride molecule, and we're given its oscillation frequency, which is, what's the natural frequency? It's 8.1 times 10 to the 13 Hertz. 8.1 times 10 to the 13 Hertz. Right. So this is going to absorb energy in units of this, but it's also, of course, going to get multiplied by Planck's constant. Right. So the energy that's produced by this is going to have these values, where n is just some integer, 1, 2, 3. So the level, the successive levels are going to be separated by some hf. Right, so this delta E, the step is going to be just hf, and we can find this in electron volts or in joules by looking up the value of the Planck's constant. So I have this here. It's either 8.626 times 10 to minus 34 joules, 8.626 10 to minus 34 joules seconds, times this thing here is 8.1 times 10 to minus 13 Hertz is just 1 over seconds. Right, so this goes away. That you get the answer in joules. If you use the value in electron volts, then you get your answer in electron volts. Obviously, this is going to be a very small number. Right, we are talking about a molecule here, so the more appropriate units for this is actually electron volts. So you might want to use the value of Planck's constant in electron volts. It's 4.136 times 10 to minus 15 electron volt seconds, and of course the frequency remains the same. And as you see, in this case, you are going to get something still small, but something more reasonable, something closer to unity. Right? So this is a straightforward application of the idea of energy quanta. This is an oscillator. It can absorb energy in only certain values of energy, and it's given by this, right? So our one packet of energy has to have one packet has to have energy of Planck's constant times the frequency of this oscillator, which we calculate this way. Okay. So the second problem is problem 14. The human eye can respond to as little as 10 to minus 18 joules of light energy for a wavelength at the peak of visual sensitivity, 550 nanometers. How many photons lead to an observable flash? Right. So the human eye is very surprisingly sensitive. Only very recently we were able to make some devices that are as sensitive, and still even professional equipment doesn't have the same range as the human eye. It's really very versatile. The problem here is, of course, it refreshes every well, it refreshes 25 times per second. So if you want to accumulate things, human eye is not very good, but it's very, very sensitive. Okay, so how do we approach this problem? Yeah. This out. Now again, this is a application of the idea of the relationship between frequency and the energy, this time for photons. So this is problem number 14. The threshold the threshold energy is given as 10 to minus 18 joules. And we are asked at the wavelength of 550 nanometers to make the calculation for this energy. So how many photons of this wavelength would correspond to this much energy? Right? So you just calculate how many joules this would correspond to. So the energy for a photon is given by is given by h times f, which is also h c over lambda. So I generally do not ask my students to memorize any formulas, but one formula that I think everybody should really know by heart, because you'll use it again and again, is this one, right? The relationship between frequency, the speed of a wave, and the wavelength. Right, so this is something to keep in mind. So we are given the wavelength, so we want to go from frequency to wavelength, and this is how you go from frequency to wavelength. And once you do this, you can calculate this energy by using the appropriate values of Planck's constant. Again, I actually did this, and when you carry this out, it comes to 3.6141 times 10 to minus 19 joules, I think. And when you divide this out, even by the photons, you get something like 2.76. Right? So if you have 3 photons, then you're going to go over this threshold. So 2.76 photons provides you with 10 to minus 18 joules. 3 photons is going to provide more energy than 10 to minus 18 joules, and you're going to be over threshold, and this flash is going to be observable by your eye. So 3 photons is sufficient. Now in an exam, if you say something ridiculous as 2.76 photons is sufficient, then you're going to lose a lot of points, because the whole point of the photon concept is that you can't really divide them. The fractional photon is not something that makes sense. Okay. Now this is a bit out of order, but this is again an application of this basic formula. So I moved it here. So this is problem 76. Sunlight reaching the Earth has an intensity of about 1350 watts per meter square. Estimate how many photons per square meter per second this represents. Take the average wavelength to be 550 nanometers. Okay. So again, go over here. I'm not going to solve this in detail, because this is kind of repeating what we have already done. We are even using the same wavelength here. Okay. 160, so our wavelength of photons is 550 nanometers. This corresponds to an energy, again let me look this up, 3.6141 times 10 to minus 19 joules. What are they asking? So we have an intensity of 1350 watts. That's joules per second per meter square. Estimate how many photons per square meter per second this represents. So we're just going to take this. So the power is 1350 joules per second per square meter. And to convert this into photons, of course, we have to divide out by this, right? So the number of photons per time per area is going to be 1350 divided by this number here, 3.6141 times 10 to minus 19. And because this is joules and this is already joules, this is going to be number of photons per square second per meter square. Right? I'm not going to carry out this calculation. But it's always the same idea, right? The energy of a photon is given by Planck's constant times its frequency, and by looking at the light, you'll get the power in light that would correspond to energy per time, per unit, per time interval. And here, this is not actually power, this is intensity, right? So this is power per area. Yeah, you're just going to manipulate things around. Okay? I don't know how to elaborate this further, but during the recitation we can certainly discuss if you have any questions on how to approach these problems. Okay. Problem 19 is that when ultraviolet light of wavelength 285 nanometers falls on a metal surface, the maximum kinetic energy of emitted electrons is 1.70 electron volts. What is the work function of the metal? Okay, so this is a photoelectric effect, but it certainly includes this idea of flight quanta. So let's take a look at this. Problem 19. So we have some surface. There's some light coming onto this. Its wavelength, it's ultraviolet, so it's below the wavelength of the visible light, 285 nanometers. Some photons are coming, and it emits some electrons. The maximum kinetic energy, Ke max, for these electrons is very conveniently given in electron volts, 1.70 electron volts, and they're asking for the work function of the metal. So what happens here is that these photons fall onto the surface and they lead to emission of electrons, right? And those electrons, they absorb all of the energy of this photon. So they absorb this energy corresponding to this 285 nanometers, but some of them they spend on the work function of the metal, and then the rest is available to them as kinetic energy. Right? This is the idea. So the energy of the photon then is going to go to the work function plus the kinetic energy of the electrons. Right? And so to do this, we need to calculate the energy of the photon. And the energy of the photon, as we have already seen, photon is hc over lambda. And here we're going to use a convenient number. So this hc has a value in nanometers in electron volts, right? So it's 1240. This is 1240 electron volt nanometers. And when your wavelength is given in nanometers, this is a convenient way to calculate your energy of the photon in electron volts. Right, so this is a handy number to know. I mean, you can look this up. This is available. But rather than going through the separate values of these and trying to carry out a multiplication, if you keep this number in mind, or if you look it up, just the value of h times c directly, then you'll be you'll cut off some of the algebra and also some of the ways to make mistakes. Right, so you divide this out, and what you get is, well, then from this you're going to subtract off, so the kinetic energy of the electrons, sorry, the work function. So what's being asked here is going to be the photons minus the kinetic energy of the electrons. So it's this number over here, 1240 minus 285 minus 1.70. Right, that's given electron volts, so we can subtract them off directly, and we get, if my algebra is correct, it's get 2.65 electron volts, which is reasonable for ultraviolet light. You get something on the order of electron volts. So I don't know if my algebra might be incorrect, but this is how you would do this. And in particular, when you're calculating the energy of the photon, I strongly recommend that you just use the value for this product rather than going to separate values. It's a handy trick to have, and it will be useful for you, I suppose, when you're solving problems like this. Right? So you can convert this into joules, of course, but for the work functions of metals, it's typical to leave it in electron volts because that's the atomic scale, and electron volt is the appropriate unit for this situation. Okay. So the next problem is going to be problem 26. So this is a level 3 problem. We have a group of atoms that's confined to a very small point-like volume in a laser-based atom trap. The instant laser light causes each atom to emit 1 billion photons of wavelength, 780 nanometers every second. A sensor area of 1 centimeter square measures light intensity emanating from trap to be 1.6 nanowatts. when placed 25 centimeters away from the trapped atoms. Assuming each atom emits photons with equal probability in all directions, determine the number of trapped atoms. Okay, so this is a mouthful, it's a long problem. So the first thing you need to do is to understand what's going on. So let me try to start from there. I mean, even though this is level 3, I don't think it's very challenging. Unfortunately, I'm losing light. I hope this is not going to be too bad. I hope you can still see this. Okay, it's 26. So the situation we have here is we have a atom trap, right? There are some atoms here, and we have a detector that is like 25 centimeters away, and yeah, so 25 centimeters away, and it has an area of 1 centimeter square, and this measures a power of 1.6 nanowatts. 1.6 nanowatts. Okay. What else? We have each atom emits. So for every atom has 1 million photons, and the wavelength of these photons is 780 nanometers. So this will correspond to, of course, some energy, and multiplying this by 1 million, we are going to find how much energy each atom emits every second. Right? This is per second. Okay. So if you find, and they're asking us how many atoms there are, right? So the question is the number of atoms. Okay. So if you can find the total power that's emitted from this trap by dividing this by the power emitted by a single atom, we can find the total number of atoms, right? Because the power of a single atom times the number of atoms should give the total power. Now what we have here is part of that total power. 1.6 nanowatts is not the total power that's emitted, so this power is emitted isotropically in every direction, but we are seeing only a small part of this. Now what portion of this power are we seeing? Well, that should be proportional to the total surface of the sphere that is 25 centimeters away from this trap, divided by the area that we are actually seeing. Right, so what is the surface area of this trap? It's going to be 4 pi r square, and that is 4, let's say 355 by 1113 times 25 squared. It is going to be, I think I calculated this, yeah, 8754 centimeters square. Right? So we are seeing only the power that's through only 1 centimeter square. So we are seeing actually the actual power that is emitted from this trap is 7,854 times the power that we are actually seeing. Right? So the power total, P total, is going to be just this number, 784 times 1.6 times 10 to the minus 9 watts. Okay. Now what about the power per atom? That is going to be 10 to the 6 photons, and the value corresponding to this, so that's going to be H times C divided by lambda. Now we can't use 1240 nanometer electron volt because this is in watts. We are eventually going to divide these out, so we want to get this in joules, so you need to look up the value of this HC in joules, joules nanometers or joules meters, I don't know, something like that. But I did do this, okay? And yeah, so the ratio P total by P atom comes to something like 493 times 10 to the 7 atoms, right? 7. That's the total number of atoms that's in the trap. So this is a reasonable number, right? I don't know I never saw this experiment being done, but I do know that cell contains something like 10 to the 9 to 10 to the 12 atoms, and I imagine this is microscopic. I don't imagine that this will be like tens or hundreds of atoms. That will be nanoscale. That will be very hard to control. But this seems reasonable. Like this is almost like the size of a cell, small cell perhaps, and it's certainly not on the order of Avogadro's number. If you got something order of Avogadro's number, I would be very surprised. Right? If you have an Avogadro number of particles, then you can't really control them with a laser trap. That would make sense. It has to be microscopic. So something smaller than a cell but larger than nanoscale, I think that makes sense. So yeah. So this is how you proceed. You want to calculate the total number of atoms. For that you need the ratio of the total power to the power per atom. The total power you calculate from the power that's incident on your area amplified by the total area. Right? The total area is 7,854 centimeters squares. You are looking at just 1 centimeter square. So the total power through this sphere, which must be the power just emitted by this, it has nowhere to go, it has to pass through this sphere. It must be just this number multiplied by whatever you're measuring. Right? So this is the total power. And then the total power for atom is just every atom produces 1 million photons. Each one has a wavelength of 780 nanometers. So we can calculate the energy of each photon. You can calculate the energy emitted by a single atom per second by making this multiplication. And then you carry out the algebra and you get this number. Okay? And again, if you have further questions, I will be happy to try to answer them during the recitation.